Hello, Christian Kremenhoft from Liverpool. In this video I wanted to discuss some relatively interesting limit analysis problems related to tunneling. And to give a bit of an introduction, I put together a couple of slides. The first one here just to simply say that tunneling is nothing really new. It's something that's been going on for a long time. This photo is from the St. Clair River Tunnel project, completed in the 1890s, connecting Canada and the United States. And this project made use of some really, at the time, novel techniques that since have found their way, I think it's fair to say, into modern tunneling as well. A lot of the concepts we see in use here are actually used in modern tunneling operations as well. So how does it work? Well, first of all, you have the workers in here digging out the material, excavating the material, which is then transported out of the tunnel. And as the excavation progresses, then these hydraulic rams gradually place the lining. So it's a cast iron lining in this case. Modern tunnels, of course, mostly make use of reinforced concrete. And if you look at the workers here, but the principles are the same. If you look at the workers here, what is worth noticing is that they seem relatively unconcerned about the stability of the tunnel face here. And that could be because this is a good hard material, although that doesn't really fit with the fact that they seem to be digging it out with shovels. There's no pickaxes or hammers or anything like that in action. So why does this tunnel face stand up? And the reason for that is that this project made use of a really novel technique of this thing with the progressive placement of the lining, but also the entire chamber was pressurized. So it says here from 10 to 28 bar, depending on the material excavated. So that is what was used to control the stability of the tunnel face, a pressure here within the excavation chamber. And modern tunnel boring machines make use of similar ideas. I mean, the principles are really very similar, if not identical. So here's a modern tunnel boring machine, and this has been put together in a way that we have two chambers: an excavation chamber, that's the one out in front here, and then a working chamber. So the excavation chamber, the brown stuff here is supposed to represent a bentonite slurry. So the excavation chamber is full of this slurry, and the working chamber is partly full, and then there's this wall here, and the upper part here contains compressed air. So basically, by compressing the air in this upper part here, you can control the fluid pressure, which acts on the tunnel face. You can't really see that here, but it does. So the way it works is that the machine grinds away at the material, which then finds its way, soil grains find their way into the excavation chamber, and they are then dissolved or suspended in the slurry, and the slurry is pumped out, and a new bentonite is pumped in. Here's a diagram of the process. So the slurry, the compressed air, and the material comes into the chamber, suspended in the bentonite, and it is then pumped out. There's a separation of the grains and the bentonite up here at the ground level, and the bentonite is then pumped back into the chamber. This pressure out here, which is sort of a fluid pressure in modern operations, is of course to control potential local collapses here in front of the machine, which would eventually translate into settlements at the ground level, which of course is not something that's particularly desired, and also to control the inflow of water into the tunnel. So that's the way it is often done, and so this pressure on the tunnel face gives rise to two different limit analysis problems. The first question is, how much pressure should be applied in order for the tunnel face to actually stand up? So in order to prevent this situation here where you have material flowing into the tunnel, there's a minimum pressure that sees to that. Now, if you keep increasing the pressure above the minimum pressure, well, you will eventually have this situation over here, which is referred to as a blowout, where you have an instability which finds its way all the way to the ground surface, which is of course not really a good situation at all. So there's a range of pressures between what is known as the collapse pressure, the minimum pressure necessary to keep the tunnel face stable, and then the blowout pressure, which will imply a full blowout of the tunnel face up to the ground surface. And those are the two pressures that we are going to find in the following using Optum G3. So tunneling is, or this problem is really a 3D problem, and I think it should be treated as such. But in the past it's been dealt with quite extensively using 2D approximations, 2D plane strain approximations. And the question is, of course, always, what section you should consider. Is it something like this, or is it something like this over here on the right? I think this is the more popular problem to consider. There's a lot of papers on this particular problem, referred to as stability of circular tunnels or something like that, this plane strain type problem here. There's all kinds of variants of this problem in the literature with different materials, frictional material, cohesive frictional, undrained clay with a constant SU, undrained clay with a SU varying with depth, and so on and so forth. And then everything is typically repeated for a square tunnel and then a rectangular tunnel. So that has given rise to a lot of papers. But the question is really whether the results are meaningful, considering the geometric approximation from the true 3D problem to this sort of 2D plane strain problem. And we'll look at that in the following as well. So 3D analysis has also been carried out. There's a paper here that I've been looking at, Moyong, Diaz, Supra. It's a paper in one of the American journals, Journal of Geotechnical and Geoenvironmental Engineering 2013, entitled Range of Safe Retaining Pressures of a Pressurized Tunnel Face. And that's exactly what we're looking for, this range of pressures from the collapse pressure to the blowout pressure. And then they have looked at some sort of, there's a probabilistic spin on this as well, which I think is actually very relevant, because one thing is determining these pressures for a sort of an ideal homogeneous soil, but in reality, of course, there's lots of inhomogeneities in the ground. But we'll be looking at the homogeneous case as well. And as you can see where I have these figures from, that's from this paper. And we'll be looking at a model which is identical, or at least in principle, similar to this one. So we consider half the tunnel. We'll consider half the tunnel. So use symmetry considerations to only consider one half, and the pressure, the tunnel face is in here. This is where the pressure will be applied. And these guys here considered a particular case of a tunnel with a diameter of 10 meters. The unit weight of the soil was 18, and then they have different material parameter sets. So here is a drained analysis with a friction angle of 17 degrees, cohesion of 7 kPa, and then collapse pressure, blowout pressure, 4 different C on D, C being the cover and D being the diameter of the tunnel, which is set to 10 meters. They don't have any surcharge. They don't consider any surcharge in this paper. There's usually some surcharge, of course, buildings or machinery or whatever are at the ground level as well, but we will follow this paper and neglect surcharge. And so the collapse pressures and the blowout pressures, and 2 different methods. M1 here refers to what I think is fair to say is a semi-analytical method that has been sort of devised by the authors, and then FLAC 3D numerical analysis, 3D finite element analysis with a model that must have been pretty large, because according to the authors here, it took something like 50 hours to run. I hope we can do a little bit better than that, and I think we will let's look at some nice numbers. Let's look at the case of C on D equal to 2. So a diameter of 10 meters and a cover of 20 meters. And let's switch to G3. So here we are. And let's first define some geometry. Say something like this, and then I need a diameter of 10 meters. Say I want 10 meters of soil below the tunnel and then 20 meters above, so 40 meters. I don't know what happened there. So a height of, say, something like, probably like this should do, and a height of 40 meters. Good. And then I also need to, of course, define the tunnel. And how do I do that? Well, the first question is, should I use a cylinder or should I use this so-called end prism, which is a discrete cylinder? Both are possible to use, and I will try out both of them, because there's a bit of a point to that as well, exactly how you define the tunnel in this case. And that's the first question. The second question is, by default, these objects are defined such that the base is in the XY plane. How do I switch plane? Well, I can do that very easily. I need to just untick solid, and then I can select this set this as the work plane, and then of course I will have the tunnel in this direction here. So let's select the cylinder. That's the obvious choice, of course, and then we should be at 15 here for the Z coordinate. The radius is 5, and the height is, let's make it something like 30 meters. It shouldn't be too close to the end, this tunnel. So like that, and then we can delete, and here is the geometry. It's exactly this geometry here. Well, the dimensions are not exactly, or the proportions are not exactly the same, but it's the same principle, and we will have, of course, symmetry boundary conditions as well. But before I do anything, before I actually start applying material and boundary conditions and so forth, I want to just have a look at the mesh that I get, because it's always a bit dicey how, especially the base of these cylinders will be discretized, also the rest of the cylinders, because there will be an approximation, of course, and it's just a good idea to just have a look at that, because it is not too critical in this case, but we want a sort of a fairly nice approximation of this circular tunnel. And do we get that here? Well, it's not too bad. It's not too bad, although you can see that it's not really, some of the segments along the base here are fairly small, say down here, and some are fairly large. The discretization of these curved objects, cylinders, spheres, cones, and so forth, can be controlled by this quantity here in under project and mesh. There's something called a mesh angle. The default value is 15 degrees, meaning that the segments here they're sort of 15 degree segments here along the edge of the along the base of the cylinder. So we could try to change that to 10 and then rerun the analysis. And how does that look? Well, it looks sort of similar to the way it looked before. So we have larger segments, and then there's some, it's kind of nice and smooth down here, but then up here the segments get larger. So up here they're quite nice as well. So it's not too bad, but another problem is that we have a lot of elements in here where there's nothing really going on. So we would like to sort of be able to control this better, and my personal preference for this problem and similar problems would probably be to use the end prism instead. So let's undo that, and then let's try to use an end prism. Set that as work plane again, and then select end prism, and n is the number of segments that define the base of the prism, and I'll set that to 20. So I have 10 segments for the half cylinder, and again I need to be at a z coordinate here of 15, radius 5, height minus 30, and reset the view, and then delete this. So this is my now discrete circle, tunnel, and let's try to mesh again. And this looks a lot better. So we don't have very many elements along the length of the tunnel, which is kind of what we want, and we have a nice even subdivision of the base. So all the segments here are of the same size. So we'll stay with that, and let's then get moving with some material, and it is a more Coulomb material, and the parameters were 7 kPa cohesion, 17 friction, and 18, so 7, 17, and a unit weight of 18. Good, and then standard fixities. That's pretty straightforward. And then as well we have to do something about the part of the tunnel where basically the lining is, and I'm going to support these in the normal direction only. You could argue that it should be fully fixed. You could argue that you should actually put in shell elements to represent the lining. I'm just going to go for a simple and I think somewhat conservative solution here of just supporting it in the normal direction. Otherwise it would simply collapse immediately. And then a pressure here at the tunnel face. And I can just one more thing. So this would basically correspond to the blowout situation, right? Where I have a where I find the maximum magnitude of this pressure, and that will lead to a sort of a blowout. And just one last thing, because I can see we've probably not made this rectangle here, this block, long enough. So let's select this face, and then we can move this face to here. So I think that's a lot better. But we'll of course see once the results are in if this is sufficient. We don't want the failure mechanism to intersect with the boundaries, of course. And then limit analysis, and can do some adaptivity. We use the mixed element as usual, and then some adaptivity. So that's the blowout problem. Now the collapse problem is exactly the same, except the load has the opposite sign. So we applied load in the opposite direction. We maximize this load, pushing the tunnel phase into the tunnel, but the maximum value of that load will most likely be negative, corresponding to a situation where we sort of have to resist the soil collapsing into the tunnel. So that's, we could call that collapse. And then we can run. And while we wait for the results, I might just actually solve this problem in 2D as well, using this common plane strain approximation, this one here. Let's try to do that. And let me just try to adjust the grid spacing, so 5. And then let's have a rectangle to represent half the soil domain, and that should be how, 50 and then minus 40, and we have more or less the same as in the other case. And then the tunnel with a diameter 5. Delete that, apply material, and that was 7, 17 and 18 for the unit weight. And then some standard fixities, some load, and I will just do one more thing. I'll use a mesh size here on this curved boundary to make sure that the mesh, that this boundary is discretized properly, and I might use something like 0.3 for the mesh size. That I think that should be enough to get a fairly smooth discretization, and 1,000 lower bound elements. And why don't we also actually do the collapse problem? So this is again blowout and collapse, and let's run. And while we wait for that, let's go back to G3, see where we're at. Well, the collapse or the blowout problem has been completed now, about 2800 kPa. Well, and for the let's see the 2D problem. So the blowout, see, it blows out, and the collapse, well, it collapses. The 0.3 was of course more than enough there. I should have taken something like 2 meters for the characteristic mesh size around the tunnel perimeter here, but never mind. And the results are in. We can plot some shear dissipation, and that is exactly as shown here. This is the blowout. It looks more or less as expected. A load multiplier of just under 2800. So 2800 kPa here on the tunnel face, which actually is 28 bar. If you remember the St. Clair tunnel project, that was the maximum pressure they applied. In this case, that would have been sort of close to the blowout pressure with these parameters here. And there's this geometry, and the collapse pressure a lot less, of course. In this case, only about 41 kPa necessary to prevent this thing from collapsing. So 41 kPa necessary to keep the tunnel face standing up. So you want to be in between those two pressures, 41 and 2800. And let's just see what the what the 2D analysis gave. Well, for the sort of look qualitatively, it looks similar, of course. I mean, there is a blowout, the pressure, the load multiplier in this case 715, so way below the 2800, and the collapse pressure 151, which is actually quite a bit above the 41. So well, it's a factor of 3 to 4 in both cases. So is this a good approximation? This 2D approximation, is that a good approximation to the real thing? I would say not really at all. And so, well, let's try to compare our results here with what is stated in the paper, and that's for C and D equal to 2. And I, with all due respect to the semi-analytical method here, I would sort of be more interested in comparing with the FLAC 3D results, so 2740 versus our 2800. So we are a bit above this FLAC 3D solution. Probably with more elements we would get a closer comparison, but I would still consider this a success. There's not really a lot of difference, and the collapse pressure 37.4, and we have 41, so more of a difference in that case. And whether we are right or they're right, who knows? That is something that could be investigated by basically using very fine upper and lower bound measures in G3, and well, I don't know. It's fairly close. It's definitely in the same neighborhood. So I would consider this verification successful. And I think that's it. See you next time. Bye.